as you know, the subject is mechanics. What do we study in mechanics? Any answers? Physics. Physics में तो बहुत सारी चीजें आ जाती है, मतलब it's probably a branch of physics. Motion of the bodies or what prevents motion of the bodies. So basically we are dealing with quantities which are applied on a body and which tend to move the body or actually move the body, and then details of these are what we study in mechanics. But if and what are these things which tend to cause the motion? The basic entity you can say is a force. That a force which is applied, force could be applied at a point, it could be in a distributed way. We know many examples of all these things, and that is what will tend to either move the body or sometimes you see if a combination of forces is acting on a body and you want the body not to move. So then how should forces be applied so that it does not move? So all this basically motion or not the motion of a body is what is covered in mechanics. And in this course we will be covering, in the realm of this course we will have only classical mechanics. Now what do we mean by classical mechanics? That we are not in the relativistic domain. That means the speeds we are talking of are much less than the speed of light. So that space, mass and time, these are independent quantities. They do not depend on each other. So we will still talk of classical mechanics. So speeds much this is what we have now. So let's start. When we talk of mechanics, there are some very basic preliminaries, a lot of which you will know. We start with vectors, and we'll, at least at this time, I'll only write about studying vector in Cartesian coordinates and if these are our coordinate axes x, y, z, which we call the Cartesian coordinates, then if we have a point P here whose coordinates are x, y, z, we draw the position vector OP, and if we write this as vector R, then we know vector R is equal to xi plus yj plus zk, where I, j and k these are the unit vectors along x, y and z axis. Okay. So this is the position vector. Then we also can define if we have any direction, we can define a unit vector along that direction. So here what will be the unit vector along r direction, and this unit vector we define as the vector r divided by the magnitude of the vector r, and this will be equal to, so here this will be, if I write this unit vector as E, in fact I should call it ER, so this vector will be equal to xi plus yj plus zk upon square root of x square plus y square plus z square. So this is what we write as the unit vector. Then we also know, so this is the unit vector along R, and this I think you know. Now suppose if we have a point A and a point B, and I have a vector AD. If the point A has coordinates xa, ya, za, point B has coordinates xb, yb, zb. So now the vector AB, which we'll also write as position vector of B with respect to A. So this is a notation we will use for vector AB. B represents the final point, A is the origin. So position vector of B with respect to A, what will this be? And this clearly will be equal to xb minus xai plus yb minus yaj plus zb minus zak. So this is the position vector, and a unit vector along AB can be written as AB divided by the magnitude of AB, and this we can work out. It will be this vector what I have written divided by square root of xb minus xa whole square plus yb minus ya whole square plus zb minus za whole square. So this is how we will get the unit vector along AB. Okay. Now sometimes what happens is, if we want to find component of a vector along an axis and perpendicular to the axis. So that means given vector A, and then I have a line L, unit vector along which is given by E. And so what I want to find is, or let me call it E1. So I want to find the component of the vector along E1 and the component perpendicular to E1. In fact, it's the last part which is slightly more involved. The first part probably all of you know how we'll find it, and even the last part should be quite straightforward if we work it out. So now let's see what the component of this vector A along line E1, A dot E1. So vector A dotted with E1 is equal to component of A along or parallel to E1. How will we find the perpendicular component? A minus. So to find the perpendicular component, as all of you have guessed, the perpendicular component will be vector A minus A dotted with E1, E1. So this last E1 is important because you can only subtract two vectors. You can't subtract a scalar from a vector. So therefore the total vector A which you have minus the component of A along E1 along with the unit vector E1, that is what will give you the perpendicular component. And this sort of a thing is physically needed sometimes, because if you have a force acting on a surface, force may be acting along any direction. You want to find the component which is perpendicular to the surface and the components which are along the surface. Does anyone know what are the, if there is a surface and a force is acting along the surface, what are those forces called? Shear force. A shear force is a force which acts along a surface or parallel to the surface, and perpendicular to the surface what we have, that is what we call as the normal force. So Sometimes the total force is given to you, you have to find the shear force. So then from there, that is how you will work out these things. So this is how, what we are talking of, these concepts are not in abstract. Now also I think all of you are aware of, basically, so having done this, I think concepts which you already know. Dot product of two vectors, I don't think I need to go through. Cross product of two vectors, again you know. So if we have two vectors, let's just see, say A and B, then dot product, which we write as A dot B, let's say vector A is equal to AXI plus AYJ plus AZK, vector B is equal to BXI plus BYJ plus BZK. Then the dot product A dot B, this will be equal to AXBX AYBY plus AZBZ. So this is the dot product, it's a scalar, and I'm not going to go more into the, well, you also know if the angle between A and B is alpha, then the dot product would be given by magnitude of A, magnitude of B, cosine of alpha. So all those things basically are. Cross product, when we work it out, cross product again we will write it as A cross B, and this you can express as a determinant, at least for Cartesian coordinates. It works out AX, AY, AZ, BX, BY, BZ. So you can work out the determinant. But sometimes it also works out that for cross product, when you calculate, when you write the cross product, what you keep in mind is we go in a cyclic order. So if I have unit vector I, unit vector j, then I cross j will give me k. So what I mean by cyclic is I write I, j, k in this order. So if we are following the order of the arrows, then we will get a plus sign. If we go otherwise, we will get a minus sign. And for a right-handed coordinate system, so therefore we will also from here get j cross a, k is equal to I, and k cross I is equal to j. And if we have an opposite order, we get a minus sign, and I cross I, j cross j, k cross k will be 0. Okay. So now using this, in fact, sometimes, so if you have to write, instead of doing the expanding the determinant, what you can do is, if you have A cross B, you can also write A cross B in a full form as AXI plus AYJ plus AZK, and you cross it with BXI plus BYJ plus BZK, and this particular form is useful if some of the components are 0. So then you can expand it in a long notation, and the expansion will go like, work out A cross B, this will work out is equal to, we multiply it term by term. So first term will become AX BX I cross I plus AX BY I cross J plus AX BZ I cross K, and you have like this total 9 terms. I cross I will give you a 0, I cross J will give you K, I cross K will give you minus J, and so on. So and you can expand it in a long form like this also. So either you calculate the determinant or you go in a long form. Now having done all these, having done these vectors and all, then let's move on to the quantity of interest, which will be and this is the quantity which basically is what we term as a primitive quantity in mechanics. Force is something which, when it acts on a body, as somebody told me yesterday when I was in the class, that it tends to move the body. But if we look at the physical effect on the body, what does a force try to do? At its point of application, it tries to push or pull the body along its direction. So that is what force does on a body or on a particle. So force, this is a vector quantity which tends to push or pull the body at its point of application. That is what force will try to do. So now, since force is a vector quantity, in general we will write this as a vector force F, and this will be equal to Fxi plus Fyj plus Fzk. Okay. So this is basically what a force is. Now, when I say it tends to push or pull the body at its point of application. Now, because force is a directed quantity, it has a line of action. It is directed along a particular axis. Now, it turns out that a force, when it is acting on a body, you can apply it anywhere along its line of action, and it can be shifted anywhere as long as you are along the same line of action. But will this force have any effect on a point which is not along its line of action? So, for example, I have a physical body, let me say this pen, I apply a force at point 1. Now, I look at a point 2 which is not along its line of action. Now, what effect will this force have at point 2? And what we realize is, not only will it tend to push or pull the body, but also about the second point there will be a rotating effect. The force will tend to, if I am applying the force at point 1 and this is the point 2 where my finger is, I apply a force like this, it tends to also rotate the body about point 2. If you are along the line of action of the force, there is no rotational tendency. But if we are at a point which is not along the line of action, there is a rotational tendency. And this rotational tendency of a force is measured by what we call as the moment. So that is how we get the quantity called moment. So force tends to push or pull along its line of application but about any other point it also tends to rotate, and the rotational tendency of a force about a general point is quantified by a quantity called moment of the force. And how do we define the moment of a force? So first of all, whenever we talk of moment of a quantity, we will talk of moment of a force about point 2. We never talk of moment in isolation. moment always has to be about a point, or as we will later see, about an axis. So we talk of moment of a force about point O. So that means if I have to define moment, I need two things. What all do I need? I need to have a point O, and I need to have a force F. I have to have these two quantities, then only I can define moment of a force about point O. And then how do I define moment of a force about point O? What I do is I draw position vector from O to any point along line of action of F. So I can choose, let us say, a point A or a point B. I can choose any point. I don't need to have only point A or only point B. It could be any point along line of action of a force. Practically, if this force is being applied at a point on the body, then normally what you will take would be the point where the force is being applied. You will choose point A or point B to be that point where force is being applied on the body. So now moment of force about point A, about point O, sorry. So moment of force about point O, this is defined as OA cross F. Okay, so this is the moment of the force about point O, and this you will realize this is also equal to OB cross F. So I choose this vector OA, I choose this vector OB, because why is this OB cross F? Because what is OB? OB is equal to OA plus AB cross F. And what is AB cross F? 0, because AB and F are parallel. So therefore OA cross F is equal to OB cross F. So that's why we can choose any point. Now if we are talking of we will talk in this course of two type of systems. Planar system where forces are acting only along x and y coordinates, or a three-dimensional system. Let me write this down. So in this course we will talk of, we could have a two-dimensional system or a three-dimensional system. In a two-dimensional system, forces act in the xy direction or xy plane, and so the position vector is also in the xy plane. So therefore what will happen is, when the forces are in the xy direction, position vector is in the xy plane. When we take the moments, the moment will be in the z direction. There will be a single component of moment in the z direction. Moment will have no components along x and y, because force will be it will be something like xi plus yj crossed with fxi plus fyj. So when you take the components, you will only have components in the z direction, only k component of the moment. Whereas when we look at the 3D system, three-dimensional system, so here now force will be fxi plus fyj plus fzk, and moment the position vector r will be in the, again it will have all the three components, xi plus yj plus zk. So now the moments will have all the three components mxi plus myj plus mzk. So therefore, if I talk of number of scalar components in a two-dimensional system, we will have corresponding to each we will have two scalar components of force, one scalar component of moment, three scalar quantities. And in a three-dimensional system, I will have all the three components of forces and all the three components of moment. In a two-dimensional system, calculating the moment is fairly straightforward, because what you can do is you can draw a perpendicular from the point of application of the force from the point where you have to calculate the moment along to the drop a perpendicular to the line of application of the force, take the perpendicular distance, multiply it by the magnitude of the force, that will give you the moment. But in a three-dimensional system that will also work, but finding these distances will not be so straightforward. So the best thing would be you just write r cross f and you calculate the moment using r cross f, rather than trying to work out the components along different directions, which may be tedious. So the easiest thing is write your position vector, write your forces, and you calculate the moment. Okay. Now, obviously, if we look at the direction of the moment will be always perpendicular to the force, and it will be perpendicular to the plane containing the force and the point about which you are taking the moment. So that will be the direction of the moment. Okay. So now this is moment of a force about a point. Next, let's introduce a new concept which you probably would not have done, and that is the moment of a force about an axis. So we have, this is an axis A, let's call the axis as some line L, and E is the unit vector along the axis. Now, and we have a force F. Now, this you have to look at in a three-dimensional system. In a two-dimensional system, either the force will be parallel to the axis or it will intersect the axis. In a three-dimensional system, the force could be skew. It could be neither intersecting nor parallel to the axis. Okay. So we are talking of, let's look at a general three-dimensional system. So now, how do we find the moment of the force about an axis? So what we do is we choose any point O on the axis. So I choose a point O, and once again I am saying any point O. Any point means, so that means it could be anywhere here. And then the second thing we do is calculate MO, which is the moment of the force about O. That's the next thing which we do. Then moment about the axis this is defined as MO dotted with E. Okay. So now, two things you could be asked to show. If I choose another point O1, I should get the same answer. I think I would leave it to you. Try to take moment of the force about the axis from point O, choose another point O1 and then show that they will be the same. I'll leave it to you as an exercise. Try to go home and try this. But now what we realize is, in fact somebody asked me, always this question is asked, when I talk of moment about an axis, is it a scalar or a vector? The way I have defined this here, it is actually a scalar. But then if you have to, but it is a scalar, but it has to be always seen with a sense that it is about the line E. So therefore if I have to express it as a vector, how will I do it? I will multiply it by E. So depending on the sense in which it is to be used, either it will be treated as a scalar or a vector. If it is to be treated as a vector, you put a vector E in front of scalar component. Now the question which one can ask is, what is the physical significance of moment about an axis? The physical significance of moment about an axis is that it tells you the rotational tendency of the force to rotate the body about this axis. So if the rotation is to be about this axis, then this moment will not be 0. And if the moment is 0, then there will be no rotational tendency about the axis. And the easy, one very practical demonstration of this one can look at is if we look at the door. If I look at a door, the door is hinged along its vertical axis. On the door, let us apply a force which is parallel to the axis. That means I apply a vertical force on the door. Will it tend to rotate the door about the hinge or no? It will not. Secondly, let me take a force which is intersecting with the axis. I apply a force on the door in such a way that it intersects with the axis. Will this force rotate the door about the axis or not? No. So therefore, I have also demonstrated two things along with this. A force which is parallel to the axis, its moment about the axis will be 0. Can we see it from here? So basically what we have is, this is equal to R cross F dotted with E. So now the axis is E, force is F. If force F is parallel to E, then R cross F has to be perpendicular to F. And if R cross F is perpendicular to F and you take a dot product with E which is parallel to E, F, that means this will be 0. So a force F is perpendicular to E, its moment about the axis is equal to 0. What about a force F which intersects L? If the force is intersecting the L, then I will choose obviously the point O as the point of intersection and its moment itself will be 0. So then this also the intersects. So in this case also the moment about the axis is equal to 0. So therefore when we have this, in these two cases there will be no this thing, the forces will not cause any moment, so there will be no rotational tendency about the axis, which we have shown in the example of the door about the hinge. Okay. Now there is one more quantity about which we hear quite often, and that is a new quantity which is called a couple, and we also talk about a couple moment. What is a couple? Two equal and opposite forces. A system obviously they have to act at different points which are not along the same line of action, because if they are on the same line of action, the sum will become 0. So now that means we have, so not acting along the same line. Okay. Now on a rigid body, a couple only has a turning effect. I have not talked about what is a rigid body. If I ask you what is a rigid body, probably most of you will say a body which is not deformable. That doesn't help too much, but is there some other definition we can give to a rigid body? Distance between any 2 points in a body will stay constant irrespective of motion of the body. In a deformable body, if I look at two material points A and B, then the distance between points A and B could change. Whereas in a rigid body, whatever be the motion of the body, the distance between two material points, if I choose A and B, I mark them as points A and B, that distance will always be the same. As the body moves, the body could rotate, body could translate, the vector between A and B could change, but the distance will not change, and that is what gives me the definition of a rigid body. And if I look at the total effect of a couple on a rigid body, then because there are two forces which are acting, if one tends to pull, the other tends to push. So net effect on a rigid body in terms of push or pull cancels out, but the only effect which a couple has will be a turning effect on a rigid body. And how do we get to that? So let's see. If I show a system of a couple as F and minus F, so that means this is acting going through a point A, this is going through a point B. If I want to find the net moment due to the couple about a point O, so this will be equal to, so I have a point O, I want to find the net moment of this couple about point O. So if this is point O, I don't know right now how to calculate the moment of a couple. What I will do is I will calculate moment of force F about point O, I will calculate the moment of force minus F about point O, add the two moments together, that will give me the moment of the couple about point O. So when I do that, what do I get? I will get it as OA cross F plus OB cross minus F. So that gives me, that will be equal to OA minus OB cross F, and this will be equal to, so this is OA, this is OB, and OA minus OB cross F will give me equal to, this vector is OA, this is point O here, minus OB, so this I can write as BA cross F. And what I find is, when I have calculated the moment of the couple about point O, I just get BA cross F. Point O disappears. And what this means is that the moment of this couple about any point O in the space will be the same. And in this sense, we call this couple as a free vector, because a force, for the force to be the same, it has to act along its line of action. If I shift it to some other point, as I will show now, it will lead to something else. But if there is a couple which is acting, the net effect of this couple, the total forces will cancel out. It is just a moment. and this moment is the same about any point in space. And that is why I say, if I am looking at the total effect of the couple on a body, on a rigid body, the couple only has a turning effect, nothing else, because it's the moment which is non-zero, sum of forces is 0. Is that clear? So that is what we mean by saying a couple has only a turning effect. Okay. So now, having done this, let's now try to move on to the topic of what we call as equivalent force systems. Suppose I have a force system. Now, what I mean by a force system is that I have suppose I have a rigid body, or I could have what I call as a, before I talk of a rigid body, let me also talk of what is termed as, what do we mean by a particle? When we talk of mechanics, we will talk of the laws of mechanics. The basic laws which we know are what we term as Newton's law, on which whole of classical mechanics is based. We apply them on a particle. What do we mean by a particle? A particle is a body which we consider to be of a very small size, of an infinitesimal size, whose dimension in length in space is considered to be 0. That means it is just a single point. Now the question comes, is it possible to find a particle, or is a particle, does a particle really exist? In actual sense, a particle will never exist, because you can't find something of 0 size. But then, if you look at whole of our engineering, what is engineering about? Engineering is about, we have some situation in the real world, we want to write or we want to model this using physics and mathematics. We have maybe chemistry at some time, depending on what your situation is, but using our science, we want to model a real life situation, and we want to then make things which will have applications. Now, when a force is being applied on a body or on a point, if suppose the force is acting in such a way that it is only the force, force is being applied at different points of the body, and we want to see the effect on the body, then for purposes of some applications, we can treat this whole body to be a particle. For example, when we throw a ball and the ball is falling down under the influence of gravity, we treat the ball as a particle even though it has a finite size. But suppose if a car is moving and I have to analyze the motion of its wheel, then I can't treat the whole car as a single particle. I have to separate the wheel, and maybe when I apply things to the wheel, I could treat the wheel as, or a point where the force is being applied, as a particle. But often, and in fact that is what this whole course will be about, you will realize that there may be different particles, but in a lot of cases these particles, infinite number of particles, form what we call as a rigid body. And then we can develop equations for the rigid body from the equation of the particles. And when we try to do that, that is where, at least you would have studied a lot of mechanics, have quantities like moments of inertia coming up. Where do they come up? They come up when we go from a particle to a rigid body. For studying the particle equations, Newton's laws are sufficient. But when we combine these particles, and there is a special case when these particles form a rigid body, is what is the subject matter of this course. When the particles form a body which stays solid but is deforming, for example, I apply load on a beam, the beam bends. That is the focus of the study of the course of mechanics of materials or mechanics of solids. And when forces are being applied on a body which can flow, that becomes the subject matter of study of fluid mechanics. So these are the three different courses which we study in basic mechanics, and as I said, in this course we will focus ourselves on a rigid body. Particles and rigid body, we won't cover too much of particles, the focus will be on the rigid body. Now what I wanted to talk of was of equivalent force systems. So for example, I have a rigid body on which I have force F1, F2, so forces are applied, and also I have couple C1, C2 and C3 being applied. Now before I talk of this couple, I probably need some more space here. Let's see. So the couple C1, C2, C3, these are basically moments due to couples. So that means C1 will come because there are two opposing forces, equal and opposite forces acting on the body. The moment of that is what we term as C1. Now when we represent the moment due to couple, this moment due to couple is represented in two ways. Either we represent it by a double arrow in the direction of the moment. So for example, if the net direction r cross f of the couple is in the z direction, I will show a double arrow in the z direction, that I will term as the couple. Okay. Or sometimes, particularly for planar cases, we also represent this double arrow. Instead of putting this as a double arrow, we show it as a curved arrow in the plane of application of forces causing the couple. So these are the two. The simple forces are represented by a single arrow. Couples we will either represent by a double arrow or by a curved arrow. Now when we have a curved arrow, then remember we will follow the right hand rule. Take the right hand and we curve it along the direction of the arrow, and the direction of the thumb will give us the direction of the couple. So let me write this down. In this case, in the curved arrow, we curve the fingers of right hand along the curve, along it, and direction of thumb gives the direction of the couple. So this is how these couples are represented. Now what I was saying was, I have a system, I have a rigid body on which I have different forces and different couples acting. Now what I want to know is, can I replace this system by I want to see the net effect of all this on a point A. So given this, let's come back to this. So we have system of force. When I say system of forces, couples is implied in this. Whenever we will now talk of system of forces, couples implied on a body, and we want to find the net effect of the system at a point A. And this is what we will term as an equivalent system. That means given these forces and couples acting on the body, if I want to shift everything to just a single point A, what will be the net effect at point A because of this system of forces? Is that clear? That is what I mean by equivalent system. That given this original system, I shift everything to point A. Now, there are two components of this, what we have seen. There are two. So now, when we have to shift to point A, we have two components. A is the forces and B is the couples. Which is the easy part? Couples. What will be the net effect of all these couples at point A? Just the same. If all the couples are C1 plus C2 plus C3, at point A also it will be the same. Why? Because couples don't change. So couples is quite straightforward. For forces, let us see. So couples at point A, the effect of couples will be straightforward. It will be equal to couple C1 plus couple C2 plus couple C3 and so on. So couples don't change. Now for forces, let me do a very simple exercise. Let's talk of a single force F, and I want to find a force F acts on body we want to and I want to find its equivalent at A. So what I do is, at A, we add two forces F and minus F. So that means, let me do it with a red pen. I have this original system, I put an F, and with a blue pen I put minus F. Is this equivalent to the original system? A single force F acting at point, whatever, let me call this point as B. So this system is the same as the original system. Is that right? Why? Because these two will cancel out and I just get force acting at B. Now the red line force is just the same original force acting at point A. And what do the blue and the black combine to give you? The blue and the black give you a couple. And what is the magnitude of the couple? AB. So the couple vector is given by AB cross F. So that means this system I can write it as, so given this, what I get is that a force F acting at B, acting at point B, this is equal to or equivalent to a force F acting at A plus a couple which is equal to AB cross F, which is essentially the moment of the original force about the point A in question. So I can do this to force 1, I can do the same thing to force 2, force 3, force 4, and then I can get an equivalent system. So do we all understand now what that total equivalent system, we break it into parts. A single force transforms into what? A force and a couple. Similarly, all the forces will transform to forces and couples. So now when we look at the original system back, so I think we have basically done this. So let me go to a new page only so that we don't. So that means for a system of n discrete forces, F1, F2 and so on, Fn, in between let me call the general forces Fi and Fn. That means I call it as F sub I acting at R sub I, and there are m couples Cj, that means I have C1, C2, Cj up to Cm. Does everyone see this notation? I am using I for a general force. So I say F1, F2, Fi, and the total number of forces is n. And similarly for the couple, I use J as the general notation. I don't use I, so there is no confusion. And I call a couple Cj, that means I have couple C1, C2, Cj up to Cm. They are total of m couples. It's possible that m is 0, only forces are acting. It is possible that n is 0, only couples are acting. Or there could be one force and one couple. This is the general notation. Not to confuse you, but just to make things more general. Sometimes when we write things like this, people get scared because big formulas come, there are summations and all these comes. But that is just to make things sort of mathematically perfect or to include everything. So we have a system of n forces and m couples, and here now, so now we want to find, so now the moment sum of the system about a point B is equal to, I am just calculating the moment sum, this will be equal to sigma I goes from 1 to n Bi vector cross Fi plus sigma j is equal to 1 to n Cj. So that means what I have, let me draw this cartoon again. I have at point 1 I have force 1 acting, at point 2 I have force F2 acting, at point 3 I have force F3 acting, and I have C1 up to Cm, m couples acting. Then if I have a point B on the system, then the total moment which I will get at point B will be B1 cross F1 plus B2 cross F2 plus B3 cross F3 plus sum of all the couples. And then what I can say is, this is the net moment sum, and the resultant of the force system or I can also call it as the equivalent of the force system at point B. This resultant now is always at a particular point at point B, This has two parts. Part A is a force which is equal to sum of all the forces I going from 1 to n, and part B will be a couple resultant which is equal to sigma So this is how an equivalent force system at any point will come. As I said, the two part whatever forces are acting on the body, you take the vector sum, make it act on that point. That's one part. And the second part is a couple which has basically all the moments of all these forces about the point B, plus if there are any couples in the system, you add them up. And that will be the net equivalent at point A. Now, we have seen this, but is there a practical application of this equivalent? Let us think at something which is embedded in the wall. Suppose in the wall I put in a line, let me put a structure, let's call it a beam. A beam means basically something which is long with cross-sectional area, or cross-sectional dimension is small compared to its length. And on the beam we apply some forces. Okay. Now, if I look at the foundation where the beam is fixed to the wall, whatever are the forces and couples which are acting on the beam, its equivalent on the foundation will be the equivalent force system. So if forces are acting, if couples are acting, then wherever the beam is there on the wall, at that point these forces and couples are the equivalent forces. That means that wherever it is struck, it should be able to provide a resistance to these forces, otherwise it will start to move. It should be able to provide not only the resistance to forces, it should also be able to provide a resistance to the couple. Because if the couple resistance is not provided, it will tend to rotate. And that is the difference between what we say if there is a pin joint or if something is fixed in the wall. You have something fixed in the wall, the fixed thing also provides some moment resistance. Whereas if there is a hinge type of a thing, if a rotational tendency is there, the body just rotates about the hinge. It does not stay fixed. So these equivalent forces are what is the net effect, what you are putting on the body, what is felt at some other point, and if that point is a fixture, the fixture should be able to provide strength so that the body doesn't deform, if that is what your aim is. Okay. So this is how we look at the equivalent forces. Now there is just one part of the equivalent forces which I have not done, and that is we have looked at, I will do that in the next class. Today we have looked at resultant at any general point. Now what may happen is that for some special cases, one is a case of a parallel force, other of course forces are all parallel to each other, or second is a case when forces are in a plane. Then it turns out that there will be a particular point on the body where the net resultant is just a single force, and that is what we call as the simplest resultant. For example, when we talk of weight of a body, how do we account for it? A single force acting at center of gravity. Whereas actually if I look at the center of any point on the body, each of the force may cause a moment. But at center of gravity happens to be that special point where the effective or the simplest resultant is just a single force and CR happens to be 0. So this is what we will study in the next class. What is the simplest resultant? Can we always find a simplest resultant to be just a single force, or can we not? And we will show that in a general case it will not be possible to find a simplest resultant as a single force. there we will get a couple, whatever is the part of the couple which is perpendicular to the force, that can be accounted for by shifting the force. But if there is a part of the couple which is parallel to the force, we cannot get rid of that. So the simplest resultant for a general system will be a force and a couple parallel to the force. Do you see that? Or that I will explain. But one thing we have to keep in mind, when we talk of simplest resultant, we seem to be very happy we have got rid of the couple. But then it has to act at a fixed location. You can't shift the location. So in that sense, you have not got rid of any extra unknowns. While you have got rid of the couple, but then you have to put it at a particular location. So that location now you can't change. Whereas in this formulation, you can shift the location to anywhere, it doesn't matter. One last thing here. Suppose you have found the equivalent of a system at a point A, and now you want to find the equivalent at a point B. Do you have to do this exercise again? No. All you have to do is shift from point A to point B. And now when you shift from point A to point B, you only have to shift a single force. And the couple will be basically what is couple resultant at A plus BA cross FR. So you can shift, once you have found the equivalent at a point A, finding the equivalent at a second point is quite straightforward. You don't have to take moments of individual forces again. You just shift it from one point, whatever is the resultant at point A is just a single force and a couple. Couple will get transmitted as it is, and the force will get transmitted as a force plus a moment. And you add these two, you will get the resultant at a new point. Okay? So that's it. So now also I think I should tell you the homework problems for this week. For the first week we will be doing in this sheet serial numbers 1 and 2, that is chapters 2 and chapter 3. So from chapter 1 the problems will be 70 and 121. I will give you 2 problems from chapter 1 as homework, which you have to do on a sheet of paper and submit. And from chapter 2 the homework will be 19A, 53, 94 and 157. So total of 6 problems. I'll repeat the numbers again: 70, 121, 19A, 53, 94, 157. So these will be the homework. The homework will be due on Wednesday. I'll tell you the room in the next class. Hopefully by Wednesday your tutorials will be over. Okay, Wednesday tutorial 3 to 5. So maybe I can. I think this is a simple sheet of this exercise you should be able to do. So even if you're, because today you will have today at least in the tutorials the teacher can start solving the full set of problems. Okay.